time we are going to say how we spend this year. Before we model FK plus N so this are the equation figure of with A, right? Plus theta. Okay, one dimension, but dimensional. They are okay, constant. But if later on you look at this kind of matrix vector matrix the two dimension F is a single vector. G is a vector. N is a is a right and taking some noise also. But this signal makes it vector for optimize. So before we go to detail, we have to tell you how you think about this problem here. So let's so in image processing, we have a matrix vector form. So how we do that one? So let's go right from one dimension version. From one dimension. Okay. So one dimension is easy to see. Okay, it's a vector. Okay, one vector. So we can write our signal is like this. Combine with your degradation model here plus M. Okay. So it should be very easy. So every G is a vector. F is a vector. H is a vector. Also, your additive noise is a vector. Only one dimension. So if you write our definition for the convolution, we have this one, right? Remember the definition? So we have a new parameter here, k from m minus 1. So let me ask, if we have this vector with a dimension of 3 or 3 component here, and the 2 component for your degradation vector. So can you tell me what's the result of each vector size dimension? Okay, let's assume you have a F0, F1, F2, 3 components in your F vector. And we have H0, H1 degradation model, 2 in this. So what's the size of G? How many components? So it's a convolution signal processing. Okay. So you just the process is you have to do is reverse one vector and then come from infinity to positive infinity. So if they have overlap, you stop. Then sum up together. So the definition is like this one. Remember this Fk times Hm minus k plus eta m. So this is convolution definition, right? reverse, multiply, summation. Next step, reverse, multiply, summation. So it's some definition of the convolution, please. You have to know this before this class. Okay, so it's a convolution equity. Okay, let me write down clearly. So let's pull out all the components of the G result. So you can see it should be G0, the first one. The first component of the G, it should be what? M equal to 0. So it's summation K0 to M minus 1. So I'm asking what's the M size of this G vector, capital M? Actually, it's the size of H plus size of M minus 1. 4. The result should be 4 component your result. Okay, just maybe you can try later. Okay, so let's see if M equals 0, what's the output of G0? And what's that result? So it's Fk times 0 minus K plus eta M. So you can see, please derive all this detail of this summation. So it becomes what? F0 H K equal to 0 plus F0 K equal to 1 K equal to 1, and H0 minus 1 is become H minus 1, and plus what? Plus F2 K equal to 2 and H minus 2, and plus F, it should be 4, okay, because it's 2 plus 3 minus 1, so there should be 4 components. So it's F3, okay, and it's H minus 3 plus eta 0. Okay, you can see there should be 4 items like this. So the convolution, the size of convolution should be like this. Okay, if your vector size of a 3 convolve with the vector size of 2, the result should be size of 4. Okay, the capital M equal to 4. So this 4 is from 0 to 4 minus 1, 0 to 3. So K is 4 here, our example. 4 minus 1, so it's to 3. So it's up the result. What about G1? N equal to 1. What's the output of your G vector at component index 1? So what's the result? So you just use N here, put 1 here, and K from 0 to 3. So the result, if you write out, is from 0, H 1 minus 0 plus F1, H0 plus F2, H minus 1 plus F3, H minus 2 plus eta 1. Okay, blah, blah, blah. So you can write by yourself G2 and G3. Okay, actually, if you write all this content, all the details, you can see there should be formulated as a matrix. As a matrix. How? Because we have all these detailed component for each one. So I can write up like this one. G0, G1, G2, G3. As we know, because your original signal has 3 components, and your degradation model has 2 components of the vector. So the result should be 3 plus 2 minus 1. So if you have an N, you have an N for your degradation model, it should be N plus N minus 1. Okay, so if you write up all these components clearly, and you can write up this like a matrix format here. And here we use F0, F1, F2, F3 plus eta 0, eta 1, eta 2, eta 3. So there is a matrix here, H matrix. So we call it matrix vector format. So you see, it's original one-dimensional signal. So okay, please put this content here. You can see F0, the first one, the first raw data should be H0 here times F0. Okay, the matrix operation. Okay, and the second one should be H minus 1. The third one should be H minus 2 and H minus 3. And this one should be H1, H0, H minus 1, H minus 2. And this one should be H2, H1, H0, H minus 1. It's a shifting. Okay. Actually, we call it a circulant. Okay. And this one should be H3, H2, H1, H0. Okay. Let me add one more page. Okay. Is that okay to here? We just derive by definition of convolution here. Vector convolved by vector. And you extend all these output component. G0 was output content, second, third one, fourth one, and we know we can pop up like this. So vector divided by convolved with vector. Okay, so original we have a G vector equal to F vector convolved H vector plus eta vector, right? This is the traditional way you look at your signal. But convolution, you just derive it and then step by step, and you can pop up all the definition here. You can see, oh yeah, this four output. I can write up like this matrix form. And the result, what's the result? What the result is like? I can see become what? Become H0, H1, H minus 1, H minus 2, H minus 3. So I'm not going to write again. Okay, this is H0 here. This is H1 here. And this is H minus 1, H minus 2. I want you to look at this one because you know H vector. There's no negative index in this signal. So H minus 1 equal to 0. H minus 2 equal to 0. So you can see this pattern, 0, 0, 0, 0, 0. And this is H1 here, H0 here. This is H minus 2. So H2 here, H minus 1 here, right? And this is H1, H0. Okay, so why I write this one? Because you know, I told you the H is only dimension of 2. H is dimension of 2, only here, only H0, H1. So H2 is 0. This one is 0 as well. Okay, this one is 0 as well. H3 is 0 as well. So if you see this matrix, here are 0, here are 0. It's just a bend, a curve in your resulting matrix. Although you write like this one, and this is the F vector, and plus eta vector. So it's become very simple format. What's the format? Our G vector. Original, it should be H convolved F plus eta. But after your derivation, step by step, and then pull out all the 0 items. So it becomes a matrix here, H times this vector, F plus eta. So that's the reason I told you later on you will see a lot of like this one. Right? So it's not a convolution component there, right? I didn't put a star anymore. I transfer it to a matrix vector multiplication form. Agree? Can you accept this one? It's just step by step by mathematical definition. I just open the convolution here and then get this one. Okay, so especially H is a circulant matrix. What's a circulant? It's recursively. So you can see here's H0, H1, H0, H1, H0, H1, H0, because my H vector only has 2 components, 0 and 1. So it's a band and it's circular. And you ask, how about this one? Why there is not? Let's suppose if it's circular, is circular condition. This should be H1, right? If it is circular matrix, actually you can put H1 there without any effect. Why? So what's the F here? What's the F here? F is a 4 component, right? We have a 4 component. Actually, it should be 3, but during your convolution, we can add up. So it's a F0, F1, F3, F2. I told you at the beginning, F is 3 component element. So there's no F3 here, which means there's 0. We just 0 paid in there. Because our result have to be 4 by 4 for this matrix. So you put a 0 there. So please tell me, what's the result if there's any component here? What's the result for the multiplication? Nothing effect. So here we can put H1. Actually, F3, F minus 3 equal to H1 here. So you can put H1. So it becomes a real circular matrix. H0, H1, H0, H1, and then circulation. Okay, so I'm not going to go to detail of this one, but just remember, this is a circular matrix. For this operation, convolution operation. So equal to what? Our original one is G equal to H convol F plus eta, right? But I'm going to transfer this mathematical formula into what? Into a matrix vector format like this one. Okay? So this is for 1 dimension vector, like a speech signal. Now you are asking me, we are doing image processing, dimensional at the beginning. What's the result? Can you do that for this one? Actually, it's the same. But how you do it? You have to decompose your image. So we have a G M N equal to H M N convol with F M N plus eta M N, right? Be our spatial domain, 2-dimensional vector, 2-dimensional not vector, 3-dimensional matrix solution, and also eta 2 dimension. How can you do that one? Transfer to the same, exact the same matrix vector format. How can you do that? If you didn't transform to this format, our following optimization issues become difficult. Otherwise, we can do it. How can we do this one? We have a G matrix, right? It's a M by N. What's the M by N means? M rows, N column. Okay. So how can you do that? Become a vector. So the easy way is do some row-wise transpose. Row-wise transpose. So the G vector, a G matrix become what? This one become G vector. So we just take every row, become transpose, become a vector. So it becomes like this. It's also a vector. Okay. So the corresponding position is the same. So what's the F? F original is also image is like this one, your original image. So it becomes what? Vector. So if you have a M by N, so it's a become M N plus 1 size. Okay, so it's also row vector become column vector. Row vector become column 1 by 1 stack up. So what's the size of H? We call it a broad circular matrix. It's also circular. Okay, if you have a time, please step by step, like previous, we are 1 dimensional. Do it, and this become M N by M N size for this big matrix. But this matrix always is sparse matrix, so the computation is very efficient. Nothing effect. Okay, so again, we have this for 2 dimensions. How you do it? Please perform row-wise transport, and become a column vector, stack up together. So just like every row vector become transport, okay, become column vector. Put there, the same is a broad circular matrix. Okay, so previously we have a circular matrix, but now for a two-dimensional image, also we have only this format. Vector matrix H times vector F plus vector eta for the image processing. Okay, so now you can see why we can write directly. Nothing in spatial domain use convolution. So in your memory, it should be like this one, right? We say in spatial domain, we are going to do this one. In a spatial domain, we are going to do convolution. It's fine, but we can remodel this formula into matrix vector format. Okay, so please accept. Later on, we are going to use this matrix vector format in our mathematics derivation. Okay, so this is the first issue we have to tell you, because you are going to look at this one and you see, oh, there's issue for this degradation equation, and why our image is not convolution. So the student have asked me, and originally it should be operation, it should be convolution for these two degradation model and your image. How can it become like this matrix multiply a vector? So now you know the detail. We have to do some transpose operation there, and then use some circular matrix to cover it. Okay, so that's the definition first. So the next one is I'm going to ask in your calculus background. So you have a signal processing background. Now we need your mathematics background for optimization. So can you, first of all, I want to ask, can you compare two vectors, the size of a vector? Which one is bigger? So let me ask. Can you tell me? Now I have two vectors. Can you tell me which one is larger, which one is bigger, which one is smaller? Can you compare for a vector? Can you compare? Because later on we have a lot of vectors. We have to optimize. When you want to optimize, you minimize the error, minimize the variation, right? You have to compare. How you compare these two vectors? Can you? If you cannot, how can you do? Have you ever heard about norm? In Chinese, 范数. Okay, did you know that one? So there's two vectors you are going to compare. So the norm is a way to measure, to transform your vector, your matrix into a scalar quantitative value. And now you can compare. So the most famous is Euclidean norm, the most famous one. And also there's some Manhattan norm. So we have a norm, we say it's arrow norm. Arrow norm, okay. Try to transform your vector or matrix into a number. So how you do it? So we say arrow norm. The first one, the most popular is arrow one norm. What's the arrow one norm? It's a Manhattan distance. Okay, transfer your vector into Manhattan distance with presentation. So the definition is x is the vector. So we take the, okay, if x vector is x1, x2, okay, it's a vector. We are going to transform this vector into a scalable value. So how you do it? So we have used norm to represent different vector or different matrix. So the L1 known is like this one, Manhattan distance. So it's just like the original origin, your location, S1, S2. If you have two dimensions, it's easy for you two dimension plan plot, and then your S1, S2 is the location of in S direction coordinate, and X2 is the Y direction coordinate, and that's the location. So how you go from origin to this point? So Manhattan known is tell you use the rate vertical distance. Okay, the city graph distance. So it's become what? So now you can compare these two. For this example, the L1 known is become what? 3. And this one, L1 known, become 4. Nice one, positive. This absolute value, and then the result will be 4 for the second vector. So now you can compare because they're L1 known different, right? Now you can compare. So what's the known? The characteristics of the known must be non-negative, must satisfy tri-inequality. Okay, that's the and positive definite. Okay, there's 3 characteristics for the known. Okay, so just check the mathematics requirement for the function, transform your vector matrix into a known, and have to satisfy these 3 conditions. The second one is the most famous one is the L2 known. So it's Euclidean known. So it's easy to say the X vector or matrix can be derived by what? Euclidean known is S1 squared plus X2 squared. Okay? So it's just direct distance. So every vector, you can calculate the distance of your vector with respect to origin. So S1 minus 0, take square. S2 minus 0, take square. So for these 2 vectors, what's the L2 known? So L2 known for this one become what? Root of 5, right? So that's the distance from this one point to origin if it's a 2-dimension plane. And so better write this way. Minus 3. So now you know L2 known is what? Root of 10. So which one is larger? Second vector is larger than the first vector. Okay, either you use L1 known, L2 known, all the same. And we have 4 different types of known. It's L infinity known. Infinity known. So now you know infinity known is take a maximum value, maximum absolute value. Okay, so it's you can write. Sorry, it should be write one known here. X vector for infinity known. So it's exactly the same max of I. Which one? Of xi take absolute value. So all your vector component take absolute value, take the maximum one to replace the non-infinity known. So for this one, the infinity known, it becomes 2. Infinity known is 2, positive. And for this one, minus 1, minus 3, infinity known. You write infinity known, it becomes what? 3. Again, the second vector is larger than the first vector. Okay? So for the fourth one is P known. So what's the P known? The P known is definition of this every component take power of P power and then take the root of the power again, the P again. So it's become what? Become it should be right like this one. S1 should be like this. X summation of xi P power P. And then everyone take it together, summation, and then take 1 power of P. Okay, it's called P known. It's general case. But I think most of the time we use L1 known or L2 known. So if you do it in the AI, every machine learning algorithm, you need to know the known operation there. So now you can compare. Suppose we use the known matrix to measure the size of a vector or a matrix. Okay, matrix is the same. Okay, just become 2-dimensional. X from 0 to the largest size of n minus 1, and also for the n0 to n minus 1. So the size of all elements, you have to do it for 2 dimensions. Okay. Now we have this comparison for the matrix, for the vector and the matrix, because you are going to find the best one, and so we have to do it. Now the next problem is optimal. So how you solve optimal issue? So how can we change our problem into like this format? Try to minimize some vectors size subject to some constraint. So how you define your image restoration problem into this one and call it an optimized procedure. Okay, so let's do it one more mathematics discussion. Okay, so for optimization, we have 2 different approaches. One is unconstrained, the other one is constrained. So most of the time in this image processing, we use constraint. But what is unconstrained? Optimization. Optimization. Okay, let's use example to describe. So now I have an equation like this. I have an equation. Try to maximize this function. So how can you do? Maybe I give an example. Z equal to okay. This equation is f of xy equal to so let's take example of this one. You tell me there's a function f of xy like this one. So go back to your calculus, the first level calculus or calculus 1, optimize. So how can you do it? So you always take the derivative and then equal to 0 because you know there's an extreme value occur at that one, right? So take the derivative in 2 directions, one in x, one in y. Because I have a x direction, y direction, 2 different parameters. So it should be easy to do that one. So it's just run z to run x, okay, equal to 0, and find run z, run y equal to 0, and find all the solution. But sometimes you have to be careful. If you just look at the equation, you don't know it's a maximal value or the optimal value is a maximum plus the maximal value or minimal value because they are all extreme value. Sometimes it happens that optimal value doesn't exist because in different directions they have different shape. So we call it saddle point. Saddle point, like the saddle, you ride a horse, right? In x direction it's a minimum, but in y direction it's a maximum. So it's extreme value. It also has this condition, but unfortunately, in different directions they have different definition. Because their second derivative is one is a positive, the other one is negative. So we call it saddle point, 安点, 马鞍点. Like a saddle, you ride a horse, right? In one direction it's a minimum, in the other direction it's a maximum. Okay, we call it saddle point. So how can we do it? Can you do it quickly? Please, just do this one. So derivative to x, so what's the result? So to we say it's f of x, okay, derivative with x. So it's 2x minus y, 2x minus 2, derivative equal to 0, right? And this 2y, this function 2y, what's the result? So it's 2y, yeah, and plus 3. Sorry, there's 2y is minus x equal to 0, right? Please solve these 2 equations for me, because you have to satisfy either in x direction and y direction. So the result, if you solve it, it should be 1/3 y0. Okay, so x0 and y0 will give you the maxima point, extreme point, extreme value point, but you don't know it's a maxima or minima. So you have to do the second derivative to check it. Okay, the second derivative, the first derivative is slope, the second derivative is slope difference. So you can see it's getting larger slope or getting slower, smaller slope, and you will see it is the minima value or maxima value. Okay, so for this one, this is the optimal solution for this equation. We know there is a maxima point, but we don't know it is a maxima or minima. Anyway, so let's calculate this one. We call it delta, derivative to x twice, and xy derivative x first, and then derivative to y second, and this is yx, and this is fyy. So please calculate delta value, second derivative, the value, and calculate the absolute value of this determinant. We call it determinant, okay? Determinant of this matrix, and you can get what? If delta larger than 0, if delta larger than 0, we can see it is maxima or minima value. If it's equal to 0, it's a critical point. If it is smaller than 0, it's a non-maxima. So must be satisfy this condition. And this equation have the maxima value. So when it's larger than 0, please check f(x) is put inside this value, the extreme value. And if this is smaller than 0, we call it maxima. If this larger than 0, we call it minimum. Okay, actually this is the very straightforward mathematics. We don't do any constraint. I just give you a function. Please tell me if there exists optimal value, and tell me it's a maxima or minima. Just like this is like this point or like this point in 2 dimensions. In 2 dimensions. So you see the surface of the curve of the function because it's 2 dimensions. So it must be some surface around. But this one is the local optima or local minima for this function. So I think it's very straightforward for constraint optimization, right? So you run your calculus in the first level, they'll tell you to derivative and bring it to 0, find out. Because when derivative equal to 0, what's the meaning, geometrical meaning? Derivative value equal to 0. The slope is 0, become red, right? For a curve, the curve here, sorry, it's the first derivative. So you can see the slope. When it becomes 0, it becomes the maximum point there, right? So it's a negative. So the first derivative, you can see equal to 0. It tells you it's on the extreme value there. And then both in x direction, y direction, or in the maximum value, or just tell you the maximum or minimum extreme point. And if you solve it, you can get this result. So it's quite straightforward. Now we are going to look at what's the constraint. Now we are talking about the second approach for optimization, for constraint. Optimization. Optimization. Constraint. So let's also use example. If I have a box and have 3 different width, height, okay, and longitude. Okay, so you can see the volume of this one. Can you tell me what's the size of x, y, z, and satisfy surface A equal to a squared? So the constraint issue. So I tell you there's a function. The function is the volume of this box. Volume of box is can be calculated by the width, the length, and then the height of the box, okay, the volume. Please find the maximum volume and satisfy the condition. The condition just tell you very easy. Well, I hope this the maximum box, maximum volume box, they have the surface of A squared, the surface, the area. So this is a constraint optimization. How you do it? How you do it? So now it's not a very straightforward, only one function, and find out the optimal value and then check it is a maximum or minimum. Okay, you just do it, but now we have more constraint condition here. So how can we do? There are two different approaches. Okay, the first approach is what you can try to imagine. It's just combine this condition into unconstrained optimization. So now you have this condition, and how can I combine them together, become the unconstrained? So how can you do? Okay, so let's see the first approach. The first approach is transform into unconstrained. Optimization problem. So it's very easy. Just there are three variables. We want to change it and then remove one variable according to the constraint condition. So we know we have this surface constraint. What is the xy top surface plus the side surface xz plus yz equal to what? A squared, right? This is the constraint. Now we are going to transfer our problem, optimization problem, into one single function. There's no constraint anymore. So how can you do? So I'm going to maximize this function. However, there are three parameters and there's constraint. So I use the constraint replaced into this our objective function there. So how can you do? I just calculate this one, and there are three parameter x, y, z. Can I find out what's the one of them can be replaced by the other two parameters? So it should be very straightforward. Please do some mathematics calculation. So it's become a squared minus 2xy divided by 2x plus y. Okay, so please trust me. Okay, I have to do it earlier. So it should be like this one, z equal to this one. Okay, should be very easy. And then please replace into the z parameter into our objective function. So the v equal to what? I want to maximize the value, the volume. Now z can be replaced by what? Replaced by this previous derived a squared minus 2xy. Okay, is that right? Just replace it. Now you have your function. Our previous example for an unconstrained, the f of xy. How can you do it? Take the derivative with respect to x. Take the derivative with respect to y, and equal to 0, and solve the linear equation. That's it. Okay. So if you look at this is a constraint optimization problem, it's fine. Try. If you can replace the parameter into your objective function and do traditional way, it's an easy approach. So I'm not going to do that. Oh wow! I just gave you the result. Okay. So you can see v sy. You know it. So we just run v, run s equal to 0, run v, run y equal to 0. Try to find s, y, and you will find the z as well, because you know z equal to this one. So if you find the x, y, you can find the z as well. Okay, so it's pretty very straightforward. I'm not going to do it. It's one of your homework. Okay. Actually, the result is, if you know the trick, the result s equal to y equal to z. I give you the. Do I have the? Sorry, I don't have the result put here. So I remember it should be 8 divided by root of 6 or what. Okay, try to verify by yourself. So it should not be not difficult. If you know the calculus and you know the linear algebra, you can do it. Now we want to say is the second approach. You are not going to transform your constraint problem into unconstrained. You apply the Lagrange multiplier. So the second approach, Lagrange, okay, multiplier. That's what I'm going to do in our image processing restoration issue to solve this optimization problem. Let me do a survey. You know the Lagrange multiplier in optimization problem. Please raise your hand. If you don't know it, please raise your hand. Okay, thank you. Okay, so I'm not going to survey anymore. Okay, yeah. So what's the approach? So it's doing like this. If you have this function there, like we saying, we are going to find the optima of the value, and then constrain to subject to some g of xy equal to 0. So that's the problem, right? Subject to the surface of the box equal to a squared. Now we have this constraint problem, and we are going to use Lagrange multiplier. So the step 1, Lagrange function you have to write out. So what's the Lagrange function? It's a f of xy equal to f of xy, your original objective function, plus lambda of g of xy. So the lambda here is defined as Lagrange multiplier. Okay, multiply some small parameter there. Combine these two equations, optimization object function and your constraint function together. So now we have only one function to deal with. And the step 2, to do the same. Partial derivative. Now it's partial derivative. Okay, so this function, derivative to x. So it's again, it's a ln f, ln x plus, because lambda is the constant parameter, ln g, ln x equal to 0. And the second partial derivative to y, equal to 0. Okay, so again, please find this Lagrange multiplier, find the x0, y0. Okay, I think time is up, so we are going to do it in next time. So if you can do it by yourself, that's good, because it's easy. It's just straightforward. Multiply this one, and then multiply a Lagrange multiplier, and then do some optimization approach, and then we will use this box maximum volume to demonstrate they have the same result. Okay, yeah. So after you have this background, now we can talk about this, because we have this objective function to minimize this QF. Q, you don't know what is Q. Sometimes you use different metrics there. Q, sometimes identity matrix also work. Subject to this one. Why is this one? Actually, if you remember our matrix vector format, G equal to HF plus eta, right? So we are going to take the norm of this constraint function. Now we can compare, because they have the measurement matrix. And then now is a condition there. So we are going to process this one, use our previous definition. So for this equation experiment, I have to introduce a lot of mathematics background for you. So our today's discussion is the background mathematical application background for you. Okay, so time is up. So let's stop here. Thank you.
今天主要讲的是，因为后面
要用到啊，
要用到很多
是，你没有那个的话，我后面讲你应该也都听不懂。
了解。
因为最后要这一个 branch 的导数。
哦。
So 如果课本也没讲了，课本直接就给你这个结果了。Can you find it？ 你可以自己导吗？
如果没有转的话，
什么都不知道。你连这个可能这个 equation 我刚才问你可能都不知道。行，但是我们一做完以后，很简单，答案就在那里，因为我们已经有这个 background 了，所以只要 optimize 这样做就知道了。好，
就因为
是啊，
后面会用到。
是啊，这个你看啊，这结果课本只给这个方选了，来，他没有做过程，其实这就是我们刚才在做的 Lagrange multiplier， 没有这数学你根本看不懂这个事情。哦，回去你们都没有买课本。
我们用电子书。
电子书啊，那你回去看啊，其他过程都没有，他只有想说你们应该要会，可是刚才没举手是真的不会。弄有听过吗？这个 Lagrange multiplier 你会吗？我真的很好奇。第一次听到，没关系啊，反正这个mathematics 那数那个什么 restoration 就是用这个，这叫 winner filter， 他一进来就直接到这里来了，来就这里。所以你会问我说，这不是 convolution 吗？怎么会变成这样？哪里来的？那就是因为你把它变成 matrix vector format 才会有这种结果啊，不然你这个我直接就讲这个课本就直接写这样子啊，就这样子，你们自己要知道。但是没有定义前面的那些 format， 你应该看不懂。
哦，那挖我直接问，这个是在三维还是二维？
这个啊，这个是这个 example 是三维的，它算体积啊。
因为我刚才想，
它是算体积啊。
对它
那没有 z 就是某一个函数，你的 objective function 啊。像我们这边就是你要去调整，
算微分啊，然后零的时候就在那个。
对啊，因为极值都会这样算，你要微分等于零。为什么微分等于？微分是斜率嘛。
对啊。
你斜率有值的话，就表示它不是最顶值啊。你的斜率越来越小，就表示什么？
零的时候表示
它是最大。对，零的话就是最顶点的，要平的。然后再往那边就变负的。你如果知道说它二次微分是正的话，那是什么？如果二次微分是正的，就是越来越小，所以它是 minimum。如果二次微分是负的，那就是 maximum。
对，像刚刚有讲到二次微分吗？
对，有啊，二次微分，我们delta那里就二次微分，就判断它的极值是 maximum 还是 minimum， 就要二次微分了。你光一次微分看不出来，二次微分才看得出来。delta， 我刚才有一个定义 delta 那个地方，函数的 delta。啊，我怎么会加到这里来？哦 ，sorry， 反正就是 delta 有没有 ？fxx、fxy、fyx、fyy 那 delta。不是，在前面。我刚才有写了 delta， 拜托你再回去看一下 delta。就 delta 的定义，它的那个这里，它还是要看二次微分才知道是斜率越来越小还是斜率越来越大。就是在看它是这样的弧度还是这样子的弧度。如果是这样的弧度，就是它的二次微分是正的，那它是 minimum value。如果二次微分是负的，那就是表示它是往下的，正到负的，那它就是 maximum value。所以是看这个当然这个 delta 如果等于零 nothing， 然后就是可能是安点。安点就是你不能讲是最大还是最小，不是安点，就是起码那个马鞍啊，前面是这样子的，前后是这样子的，知道吧？知道我在讲什么吗 ？Saddle point。洋芋片，洋芋片没有，洋芋片只有一边，洋芋片还是只有一边，马鞍是这样子啊。在坐的地方，这边是这样子，你才坐得上去啊。前后一定这样，你才跨进去啊，没错吧？所以前后是这样子弧度，可是你坐上去的弧度是这样子，没有骑过吗？
看到，我知道这是。
那就是安点嘛，那叫 saddle point。我们数学讲 saddle point。对。
请问一下，就是那个关于那个
报告，那个领域是
没有限制，
没有限制啊，
没有限制。